Okay, now we're going to take a look at testing claims that compare two populations to one another. And we're going to start out with testing a claim about one proportion to a claim about another, and this is the notation. P is the population proportion, N is the size of the sample, X is the number of successes in the sample, successes being the occurrences that match whatever we're interested in studying or comparing about these two population proportions. And then the sample proportion, shown here, p hat, is the number of successes divided by the size of the sample, and then of course its complement is 1 minus that sample proportion. And all of these come from population 1, and so they have the subscript 1 for each of them. And the same notation applies for the other population, and we'll call that population 2, so it has a subscript of 2 for each of its notation symbols. Now here's a new one, the pooled sample proportion. To get the pooled sample proportion, we add both of the number of successes in the sample from one sample and the other, and we do the same thing for the sample sizes. We add the size of the first sample to the size of the second sample, and that goes in the denominator, and so we divide this sum, the total number of successes, by the total number of values in the sample. That is the pooled sample proportion, and its complement is shown here with a Q and a bar on top. So this is P bar, this is Q bar, and Q bar is equal to 1 minus this pooled sample proportion. Requirements are going to be met for our question, and the claim is going to be that the two proportions are equal, or at least we will assume that, and that will be our null. It may not be the claim, but we're going to put that in our null because it contains equality. Well, if the first population proportion equals the second, then if you subtract one from the other, you get 0. And the formula for our test statistic is, it's a z-score, because we're testing a claim about a proportion, and proportion means z, means we use a z-score. And so P1 minus P2 is 0, and that's here, and you may wonder, well, why does this even need to be in the formula? And it's because in certain more complicated problems that we would study in more advanced statistics classes, these two might not necessarily be the same. So that's our numerator, sample proportion 1 minus sample proportion 2. And in the denominator we have the square root of the product of the pooled sample proportion and its complement, divided by the size of the first sample plus that same product of pooled proportion and complement divided by the sample size of the second population. And because we are using, because we're assessing a proportion, we will use the z-scores, so we will get those from table A2. And here's our example. We have 89 people are randomly assigned to two groups, and they are given $1. One is given a single dollar, the other is given 4 quarters. And the claim is that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. Now, a dollar is not exactly a larger denomination, but that's a large denomination, but that's what was used in the example. And I think this makes sense because we all agreed in class that if you had a $20 bill or 5 ones, a 5, and a 10, you'd be more likely to spend the smaller bills and less likely to break the 20. People don't like to break larger bills. That's what this claim is about. And so we're going to use a significance level, it shows here, of 0.05. Now, here's our data. We have 46, that's the sample size for the first group. We have 46 people given a $1 bill, and they had an opportunity to buy gum or mints or perhaps candy from a vending machine. 12 of them did. In the second group, we had 43 people who were given 4 quarters, not a dollar bill, but 4 quarters. Same amount of money, it's just given to them in 4 quarters. And they were given the same opportunity, and 27 of them spent the money. So our first sample proportion is 12 divided by 46. Our second sample proportion is 27 divided by 43. Our pooled proportion then is 12 plus 27, the sum of the successes, and in the numerator, and then in the denominator we have the 2 samples of 46 and 43. That adds up to 89 as the problem stated, and 39 divided by 89 gives us 0.4382. So that is our pooled proportion. If that's our pooled proportion, then we can easily calculate the complement here in a minute or two. And so once again, the requirements are met for the question on the final. And now we get to the first 3 steps of our hypothesis test. The claim that money in large denominations is less likely to be spent can be expressed as proportion 1 is less than proportion 2, because remember, proportion 1 comes from the group that was given the dollar bill, so the proportion of people who will spend that should be less than the proportion of people who got the quarters. And so that's the claim. And its complement then is proportion 1 is greater than or equal to proportion 2. And we can write these hypotheses as so, because the complement, proportion 1 is greater than or equal to proportion 2, contains equality. That becomes our null hypothesis. And our original claim, which is that proportion 1 is less than proportion 2, our original claim, as we note here, is our alternative hypothesis. And of course, from that we can see we are going to have a left-tailed test. Because the inequality, as it says here, points left in the alternative hypothesis. And we're again going to use the z-score, and as I said before, it would be easy to determine the q-bar from the p-bar, the pooled proportion. 1 minus that pooled proportion is 0.5618. And so here's the calculation of the test statistic. The first proportion is 12 divided by 46, 12 out of 46. The second proportion is 27 out of 43. And we subtract the sample proportion 2 from sample proportion 1 right here. And then in the denominator under the radical, we multiply the p-bar, the pooled proportion, and by its complement, and divide by the sample size of the first population, which is 46, and we do the same or similar, that is, for the for the second sample from the second proportion. And taking care with our parentheses and doing our calculations as diligently and carefully as possible, we come up with a negative 3.49. So that is our test statistic. Now, what is our critical value? Well, for the z-scores, for the normal distribution, that's a very well-known value. It's on the it's on our table of z-scores. When we have a left-tailed test with a significance level of 0.05, that means the alpha is in the left tail, so the area to the left of the test statistic is 0.05, and that's well known to be negative 1.645. Now I should add that had you reversed which one of these was proportion 2 and which was proportion 1, you would come up with a positive value, but then that would have meant that you would have stated this both of these hypotheses differently. We would have had the arrow pointing in the opposite direction, and we would have had a right-tailed test. But as it is, and you would have a positive 1.645 for your critical value and a positive 3.49 for your test statistic, and we would come up with the same conclusion because the test statistic would be below the critical region. Test statistic is below the critical region, and so because it is, we reject the null hypothesis because this is the rejection region. So we reject the null hypothesis, and we again go to our flowchart to see how we word our conclusion. Well, we start with, does the original claim contain the condition of equality? And as we can see, it does not. It did not contain the condition of equality. And so then we come down here and say, well, did we reject the null or not? Well, we did. We rejected the null, and so we word our conclusion. The sample data support the claim that subjects who have that money is more likely to be spent in smaller denominations than in larger. And that's not what I read here, but that's our conclusion. I put it in different, very badly and awkwardly worded sentence. Okay, so that's comparing two proportions. And let's see